It gets much more interesting, however, when you look at the standard deviation and the variance. So let's try that. Again, the formulas are essentially the same. Population, sample. But the symbols are a bit different. For the population, the symbol is sigma squared, so that's the symbol for the variance, is equal to the sum of all the differences between the data points and the mean squared over the total number of observations. For the sample, you could do s squared, so that's the symbol there, s squared is a variance, equals the sum of all the differences between the individual data points and the mean, which is x bar, over little n. You see, it's very, very similar to the means. Very, very similar, just minor changes. You replace a mu with an x bar and a big N with a little n. Essentially, it's the same. Except, let's do some calculation. If you were to take away, so let's say 2 minus the mean of this one, which is 7, and then another 2 minus 7 and 4 minus 7, and you were to square all those, add them together, you would get 124. Over 9, which is the total number that you have, that would give you 13.78 approximately. Let's do this for the sample. So this time we'll take 5 minus 8 and 7 minus 8 and 9 minus 8, and we square all those differences like that, and we add them together, we would get 20. Yeah. And then you divide that by the total number of differences, which is just 4, and this time you get 5. This is way too small. This is a terrible estimate of that. You can see that. Here we have 7 for the population mean and 8 for the sample mean, but for the variances, these are much worse. It's 13.78 for the population, but only 5 for the sample. Our sample variance is much too small, and that is a common problem when you're trying to estimate the variance using only a small sample. And it's a problem that tends to get bigger as your sample gets smaller. We need a way of fixing this. We need to correct this a bit so that the sample variance isn't too small, or isn't that much too small. How would you do that? Well, the easiest way to make the sample variance bigger is by making this smaller. And you can see that. So if n here, for example, were 1, then this would be bigger than if n were 2. It'd be exactly twice as big than if n were 2, and 3 times as big as if n were 3. So if you want to make this thing a little bit bigger, you need to make that thing a little bit smaller. The way we've decided on is by subtracting 1 whenever you're using a sample. If you don't subtract the 1, that's called a biased one. It is a biased estimate of the variance. Biased. If you do subtract the 1, it then becomes an unbiased estimate. So let's draw that out again. Let's do that. Now remember, the population variance was 13.78. So let's do the unbiased versus the biased. So here we have a biased sample and the unbiased. These are essentially the same, except after you add up all the differences between the initial observations and the mean of the observations, in the biased you divide them by n, and in the unbiased, because you want this to be a little bit bigger, you divide the whole thing by n minus 1. That makes a difference. So let's see how much we get in that case. We add them all up, we get 20 in both cases, so we know that it's 20 on the top, over, we have 4 in the sample, 1, 2, 3, 4, that's n, but n minus 1, 1, 2, 3, 4, minus 1, that's 3. So we get 5, and we get 6.67. There we go. Now this is still not really the same thing as 13.78, but it's closer to 13.78 than 5 is. In any case, that's the formula that you use, and generally when you're trying to calculate the variance or the standard deviation of a sample, this unbiased formula is the one that you should be looking at.